Swayam Prabha. Digital India. Educated India.
So we're talking about matchings in bipartite graphs. So who all know what a bipartite graph is? Please just raise your hands. Okay. But who all know bipartite graphs? Very good. Yeah. You know what a matching is? Edges without conflicts is a matching. It can have one edge, it can have two edges, four edges. All of them are matchings. Okay. A maximum matching in a bipartite graph, the matching which has the most edges, the largest number of edges. A perfect matching, a matching where all vertices are saturated. Okay. In general, a bipartite graph need not have the same number of vertices on two sides. So many of the things that we are going to discuss will be true for any bipartite graph. Doesn't have to be the same number of vertices on the two sides. Okay. So this is a perfectly fine partition of vertices, and this is also a bipartite graph. Yeah. A vertex cover in a graph, the minimum number of vertices needed to cover all the edges. How many vertices do you need to cover all the edges of this graph? Yeah? With two. If you take this vertex and this vertex, all edges are covered. Okay? Can you do it with one? No. Yeah? So the minimum vertex cover has size 2 for this graph. So, yeah, you need 3, okay? So you understand what a minimum vertex is. That the second graph that I drew, the 5 cycle, is not a bipartite graph, but just these terms are valid for other graphs also, so that's fine. Okay. Now once you have a bipartite graph and a matching in it, so the bipartite graph might have many edges, some of those edges go into the matching. Yeah. Now the graph might have many matchings. Let's fix one of the matchings. With respect to that matching, we understand what a matched vertex is. Yeah. A free vertex, if it is not matched, it is free. Matching edge, an edge which is part of the matching is called a matched edge or a matching edge, and an edge which is not used in a matching is called an unmatched edge. Okay. So for example, we drew this graph. And suppose this is my matching. Yeah. So this is a matched vertex. This is a matched edge because it belongs to the matching. These two are not in the matching. Yeah, non-matching edges. These two vertices are, this vertex is what sort of a vertex? Free vertex. This is a free vertex. Matched vertex, matched vertex. Yeah, everything is clear? Yeah. Then I wrote down a greedy algorithm. Greedy algorithm is just try to gather as many edges as you can in the matching without making any adjustments or thinking too much. Yeah. Now, depending on the order in which the edges are examined, the number of edges that you pick up in this greedy might be different, but the greedy is never very bad, because if you look at all the vertices that are picked up by the greedy, all the edges that are matched by greedy, that actually forms a vertex cover. Was this clear to everybody? That when you run greedy, it picks up some edges. Then these vertices, they form a vertex cover. Why? Because if some edge escapes them, then greedy would have added it. Yeah, the only reason the greedy eliminated edges or chose not to include the edges in its matching was because it was conflicting with one of the existing edges. Okay? So, and how many vertices are there in this vertex cover? 8, which is 2 times the number of edges in the greedy. Yeah, for each edge that greedy gets, it picks up, it adds 2 vertices to the vertex cover. Now, this may or may not be the minimum vertex cover, okay? But whatever it is, these vertices, these 2 times greedy vertices definitely form a vertex cover. So, the minimum vertex cover can only be smaller. If you have a vertex cover which has some size, the minimum vertex cover, because the word minimum appears there, that means it is even smaller, cannot be bigger, yeah? And the maximum matching can never be bigger than the minimum vertex cover in any graph. Is that clear? If a graph has k vertices which cover all the edges of the graph, then nobody can get a matching which more than k, because otherwise they will end up using one of the vertices twice. And that's not allowed in a matching. Yeah, you had a question. You want to know why this is true. So let's try. Here's a graph, and here is a vertex cover. Sorry, don't be alarmed that I have not drawn the bipartite graph very neatly, because that is not important to the argument. Okay? So here is a graph which has edges which I have not yet drawn, and there is this shaded edge area which is the vertex cover. Okay? Now, whenever every edge of the graph touches this shaded area. Okay? So whenever you pick an edge in your matching, you eliminate one vertex of the vertex cover. The next edge in your matching, no matter how you think about your matching, can it eliminate the same vertex? Because then those 2 edges would have been touching. So each edge of the matching eliminates a different vertex of the vertex cover. So can there be more edges in the maximum matching than there are vertices in the vertex cover? Yeah, because by the time you get through your matching, you would have exhausted your vertex cover if it was smaller. Okay? So the vertex cover should have at least as many vertices as, of course, the matching can also have 2 things inside. That's okay. But each time you pick up a matching edge, you would have deleted at least one vertex from the vertex cover. Is this clear to everybody? Yeah. So everything I have written on the board. Okay. So last time, yeah. So what's the plan? Okay. So the plan is to show you an algorithm for finding the maximum matching in the array, in any bipartite graph. So you give me any bipartite graph which might have different number of vertices on the 2 sides, doesn't matter. This algorithm that we are going to talk about is going to find the maximum matching in that. Sorry? A maximum matching. Yeah, not necessarily. Yeah, the graph might have multiple maximum matchings. It will find a matching, and that will be the best size that you can get. Okay, good. And in the process, we will say something which is rather surprising about this inequality, and I'll let you think about it. Yeah. Sorry? Yeah. So I have two boxes here. Okay. These have little slips on them. Okay. So, wow. Okay. Yeah, it survived. Okay. Yeah. All right. So, yeah. So there are, I believe, 36 people in the room, 36 students in the room. Yeah. So I'm trying to divide them into groups of 6. Okay. So yeah, 6 times 6. Yeah, 6 groups of 6. But I'm going to divide them in 2 ways. Okay. So everybody, please pick one slip from this box. Okay. This will most probably be a number, and this will be a letter in the range 1 to F. Yeah. Okay. And this will be a number in the range 1 to. Yeah? No. They will take and pass the box around. Just pick one random. Don't try to get the same number as your friend. Yeah. Okay. Just pick a letter and note down your number. So number on your notebook and also your letter on in your notebook. Okay. Yeah. Just pass it on. So, and then we will play a game at the end. Okay. So, yeah, I don't know how we are doing, but we'll. So in the last maybe 15 minutes, we will use these numbers, but please write it down immediately because you'll lose the slip, and then whatever you see on your slip, you write down the number and write down the letter. Okay, good. All right, what can be more greedy than greedy? Okay, so if we already have an idea, so here was this graph. And the greedy came and yeah. So the greedy picked up this edge. Yeah. And we want to improve greedy. Yeah, sorry, only one number and one letter per person. Yeah. Okay. Yeah. So, is it okay? Yeah. So how do we improve this algorithm, this matching? The current matching has only the edge E1. How do we improve this? What can we do? So this is already in the matching. What should we do to get a better matching? What greedy did was each time it added one more edge. Yeah. But here we cannot add an edge. What should we do? Remove an edge and instead replace it by? Then the size will be the same. You add an edge, remove another, put one more edge. Sorry? Remove? Well, this edge is already there in the matching. What should I do first? Remove this and then see how do you increase the size of any set? If you remove one element and put one element, does the size of the set increase? Remove and add? Add. Yeah, so whenever you get a chance, look at your current matching and see if you can remove one and add 2. Yeah. So when would that happen? So here is a graph. Here is your current matching. Here are the unmatched vertices. Okay, here are the unmatched vertices. Now they have an edge. Now if they have an edge directly to an unmatched vertex, we can add that to the algorithm. Yeah. But if they don't have an edge, let us say all its edges and ask these unmatched edges, unmatched vertices. Now, if I can find a path from here to get to an unmatched, using an unmatched edge, then come back using a matched edge, and come here using an unmatched edge. Once again, was everybody paying attention? I went from a free vertex using an unmatched edge, traveled back using matched edge, and then traveled into a free vertex using an unmatched edge. Then I get a system like a matched edge, unmatched edge, unmatched edge, and then what should I do? Yeah, I adjust. Yeah, I make these two matched and remove that which was there in the matching. Is there any conflict? No, yeah, because these two were only touching this matched edge, and that matched edge has been kicked out. So there is no conflict. The other matching edges were anyway far away from the scene. Yeah, so this increases. Can you think of even a better idea? Like sometimes maybe this is not possible. Yeah, so this part has been completely matched. Yes, then there are some unmatched edges. So suppose I travel along an unmatched edge, come back along a matched edge. Sorry, please watch me. Unmatched edge, came back along a matched edge, but this matched edge doesn't have any neighbors here. It doesn't have any free neighbors. Yeah, but it has a neighbor, unmatched edge here. Okay, so I maybe go here. I'm giving you an idea. Later on we will write it down. Then I have a matched edge here, and maybe this one has a free neighbor. So what does the picture look like? I went along, what sort of an edge is this? Unmatched. And where did I start? Free vertex. Then I came back along a matched edge. And this had an unmatched edge. Can you use this to improve the matching? You told me that you can improve this to improve the matching. Why? Because you added 2, removed 1. What can you do here? Remove 2, add 3. That means all the unmatched edges in this path, you will make them matched, and all the matched edges unmatched. Now suppose there was, I couldn't find something like this, but I could find that's also good. Yeah, because I have 4 matched edges, and this path starts and ends in free vertices and with unmatched edges. So in this case, how many matched edges would I remove in this picture? 4. And how many unmatched edges would I add? 5. And my matching would have increased by 1. So the greedy was good, but this is greedier than greedy. Yeah, it looks around, says, can I improve? Yeah, now at some point we may not, we will find, we'll see that we will not be able to find these also, okay? And maybe the algorithm still hasn't produced the maximum matching, okay? So let me write down what our new algorithm, new greedier than greedy algorithm is, okay? So I'll need to tell you one more notation. So such a thing these things are called augmenting paths. Yeah. What augment meaning? Increase. Yeah. A method for increasing the matching, improving the matching. So what's an augmenting path? So yeah, can you help me complete this definition? A path. So please keep in your mind that what you are trying to do is improve the matching. That is our goal. Keep that as your attitude. Now, when you are given, somebody is given some matching, they maybe use the greedy algorithm and they produce some matching. Now you want to do even better. Yeah. So what will you look for? You will look for an augmenting path. But what is an augmenting path? Well, it should definitely make one more free vertex into a matched vertex. Yeah. So the augmenting path should start and end at, yeah, and unmatched, matched, unmatched, matched, unmatched, matched, and you should end in a free vertex. So such a thing, okay, my grammar is slightly off, but augmenting path is a path that starts and ends at free vertices and where unmatched and matched edges alternate along the path. Yeah? Is the definition of an alternating path clear? Okay. So now, here is the algorithm. It's called the Hungarian algorithm. In the 1930s, a lot of study of matchings in bipartite graphs was done by mathematicians in Hungary. And they came up with this algorithm. Basically, you have, I would like you to tell me what the algorithm is. Initially, the matching is empty. Yeah. So you start with the no edges in your matching. Then, what should you do? So you got some graph, no edge, no things. Oh, by the way, here is a free vertex. And suppose this is an edge. You understand? This is already a matching. And there is a free vertex here and a free vertex here, and there is an unmatched vertex of the graph connecting this free vertex and this free vertex. Sorry, can everybody see? Yeah. So is this an augmenting path? Yeah, so think like a lawyer. If this particular thing, edge, why is it an augmenting path? Does it start and end at free vertices? Yes. And on that, do free and matched edges alternate? Well, where do they not alternate? What do we mean by not alternate? That means two free edges are next to each other, or two matched edges are next to each other. So I know it's a little annoying, but I would like to consider this also to be a special kind of, it's a special augmenting path, because in this case, you add one edge and delete how many edges from the matching? 0. So the greedy algorithm that you were used to was actually a special case of this algorithm where it was looking for augmenting paths of length 1. It was only looking for edges which joined to free vertices, which is an augmenting path which has only one edge. And what have we done? We now want to say that let us not restrict attention only to augmenting paths of length 1, because that was the greedy strategy. We will go beyond greedy. We will also allow ourselves augmenting paths which are more than 1. But they must start on the left and end on the right. What is the total number of edges in an augmenting path? Is it always even or odd? Suppose you start from here and end here. Start from here and end here. After, will it be odd or even? Always odd. Yeah, because it has a certain number R of matched edges and number of unmatched edges. If there are R matched edges in the augmenting path, how many unmatched edges will there be in the augmenting path? R plus 1. Total number of edges? Which is an odd number. 2R plus 1 is an odd. Okay, good. So, all right. Then what is, so we have got a current graph and there is already a matching X in it. This is my current matching, capital X. What should I do? I want to improve it. So, sorry, free vertex. Find let's sorry. Oh, sorry, yeah. Okay, so you got this matching. Thanks, yeah. And now I found an augmenting path, yeah. It went about and this augmenting path's name is P, okay. How to find an augmenting path we will discuss. But we found an augmenting path and its name is P. So this P has some matched edges and some unmatched edges. And the number of unmatched edges is 1 more than the number of, like this is completely gone into your head. Yeah? Okay, good. Now, to improve this matching, what should you do to the matching? There are some matched edges in P. What should you do to them? Your matching is already there. Your P has also included some matched edges. What do you want to do with them? Yeah, remove the matched edges of P from X. Now that only reduces your matching even further. What would you do in compensation? Sorry, what should you add? From P into X. Thank you. Yeah. So add the unmatched edges of P to X and okay. So this is what I call the Hungarian algorithm. Start with a matching, empty matching. Repeatedly find local improvements. I'm calling this local improvement, meaning you add R plus 1 edges, remove, or rather remove R edges, add R plus 1. By how much did you improve? Just by 1. Okay, do that. I mean, do it. Now look again. Can you find an augmenting path? Find it. Maybe now this time your augmenting path is very long. Nevertheless, it removes R edges and adds R plus 1. So it improved again and improved again, improved again. At some point you're stuck. There are free vertices, Hungary free vertices on both sides, but you cannot find an augmenting path. This algorithm would stop. Has it found the maximum matching? Okay, and the theorem we will prove is that when this algorithm stops, the matching that it gets is a maximum matching, one of the maximum matchings in the graph. Yeah, no better matching exists in the graph. How do you even prove that no better matching exists? Yeah, if somebody gives you a matching in a graph, how will they prove that no better matching exists in the graph? Sorry? By contradiction. Is there something that they can show you that will convince you that no matching can be bigger than the current matching? Yeah? Is there anything that puts an upper bound on the maximum matching? Is there anything on the board that says maximum matching cannot be more than this much? Minimum vertex cover. So if when the algorithm stops, we can find also a minimum vertex cover of the same size, any vertex cover of the same size, then we know that our matching, of course, has the size of the minimum of the vertex cover that we found, but we are also guaranteed that nobody else can find a better matching, because every matching, sorry, this is a very deep point. Every matching, whether we found it or not, once we find a vertex cover, that forms an upper bound on the size of maximum matching, period. Yeah. So this algorithm, when it terminates, we will actually show that not only does it produce a nice matching, yeah, it has also produced a vertex cover of the same size as the matching that it produced, and that would guarantee that this algorithm produces an optimum sized matching. Okay, is this too abstract? Yeah, is that okay? So maybe let's do an example. Yeah, so, or, yeah, so I'm just wondering what we should do. We are running out of time. So does everybody have a slip? Yeah. So, you don't have a letter? Oh my God, how did that happen? It must be hidden somewhere. Sorry, these are numbers, right? There was a number in this. Okay, we'll find out. We'll find. Okay, so yeah. Let me then. Okay, so write that down. Yeah. I don't think we. Okay. So let me, sorry, yeah. Does everybody understand this algorithm? Yeah. So how do we run this algorithm? Here is a big graph. And at some point, we have this matching. So these are matched vertices, and these are free vertices. So there is certain number of free vertices here, certain number of free vertices. Is this clear? Yeah. Now, you direct all your matched edges, put arrows on them from right to left. And on free edges, sorry, unmatched edges, the dotted edges, you put the arrow from left to right. Yeah. There may be here, and there may be here. Yeah. So these unmatched edges, you put the arrows in this direction. Is that clear? Yeah. So it's totally abstract. Don't pay much attention to the actual edges I have drawn. It is some messy graph in which I have found a matching, and then there are some unmatched edges. And all unmatched edges I have directed from left to right, and all matched edges from right to left. Now, if I can find a path in this graph from any vertex to any vertex following the arrows, it would be an alternating path, because I will have to start with a unmatched edge, because no matched edge goes in this direction. Then when I return, I will have to return on a matched edge. But then when I have to come this side, unmatched edge. So yeah, you do this, you try to find if there is an augmenting path from this. But suppose there is no augmenting path. Yeah, what would happen? Let us just see. Yeah, so what can I erase? Yeah. Sorry, yeah, so please pay attention, just 5 minutes and we'll be done. Yeah, so look at the free vertices on this side. And find out all the vertices on this side which can be reached from these free vertices by alternating paths. Meaning, in this graph with these directions. Find out all those points which can be reached from here. Yeah. So let me call this A. These are points that are reachable from yeah. What do I mean by reachable from A? In this graph. Now, you also mark all those vertices that can reach B. These can reach B. All right. Now, can there be a matched edge where both endpoints, where this endpoint is reachable from free and this endpoint reaches B? Sorry, the right endpoint is reachable from A and the left endpoint reaches B. When the algorithm stops, can that be the case? So suppose there is an edge where a free vertex, this can reach a free vertex after doing some work, and this vertex can be reached from a free vertex. If this vertex can reach a free vertex, and this vertex can be reached from a free vertex, then the algorithm would have run once more because it would have done this, and reached here. So the fact that it has stopped, the algorithm is not able to find any more augmenting paths. That means the matching edges that this is touching, and sorry, the matching edges that are reachable from here and the matching edges that are reachable from there, they are all completely disjoint. Okay. Now there might be some more matching edges which are neither reachable from one nor reachable from the question. No. Okay, so how to find the augmenting? Oh, each time you augment, your augmenting path increases, your matching increases by 1. So how many times can you augment before you get the maximum matching? Well, if the total number of edges, I mean, if there are n vertices, you cannot augment more than n times. Good. Okay. So now, yeah. So all the edges out of these free vertices must be going into this part. All the edges from free edges from here to here must be going into this part. Yeah. And there cannot be any edges, free edges of this kind, because then even this vertex would have been reachable from this free vertex. Okay. So now you pick these vertices, and any vertices here. Yeah. These cover all the edges. Okay. So this shows that when the algorithm terminates, you have a vertex cover, yeah, of the same size as your current matching. And whenever you have a vertex cover, see, a vertex cover is always bigger than maximum matching. But if you can find a vertex cover and a maximum matching of the same size, then it must be the optimum matching. Every matching is greater than, every matching is less than or equal to the size of a vertex cover. If you can find a vertex cover of the same size as a maximum matching, then your matching is certified to be an optimum matching. Okay? So that is the principle. I'm running out of time. So anyway, now your question was, how do I find an augmenting path in this graph? Okay? Well, you find out which are the reachable vertices here. Then you understand who are the reachable vertices here. Then you understand who are reachable vertices here, who are reachable vertices here, and ever you get down. So I'll let you think about it. It's not one of those combinatorially explosive processes to find whether there is a path from here to here in a graph. This is a reasonable process. Some of you have done some programming or some graph theory. You've done depth first search. How many of you have heard of this depth first search? No, good. Okay, good. So things like that can be used to find an augmenting path in this graph. Okay, so now, so we can finally do our thing. So the problem that I want to solve is this. I don't know if we have time for this, but good. Yeah, I know. Okay. Yeah. So we have how many groups? Numbers? 6. Yeah. So 1, 2, 3, 4, 5, 6. So there are 36 of you. Some of you have received 1. Some of you have received 2. Some of you have received 3, 4, 5, 6. Yeah. Okay. And now some of you have received letter. Everybody has received letters, and the letters are A, B, C, D, E, F, and G, and sorry, E, F, F, F. Yeah, I can't count. Yeah, good. 6, yeah. All right. So I don't know if we will have time for this, but let me tell you what I want to do. Yeah. So I will call upon all of you, and you have to write half your name based on your number. If your number is 1, you have to write your name here. If your number is 4, you write your name here. Okay, so all 36 names will be here. Sorry? Something is wrong? Yeah. And similarly, all of you will have to write your names here. 36 names here, 36 names here. Now, where is my bag? Where's the bag? So the point is this, yeah? So one of your teachers has decided that she wants to split you into six groups of 6 each, yeah? And there'll be some students. But the other teacher has a different idea, okay? She wants to split your group like this, okay? And I have a totally different idea. I have got these hats of 6 colors, okay? Understand? Yeah, so there are 6 different colors, and everybody has to be given, I'll give you 1 hat. But I want this, that in every group, everybody should receive a different color, okay? Now this person, I give you these hats, you should all get different colors in each group, and I make you stand according to these groups. So everybody has 6 colors, okay? Then you hold on to your hat, you can't exchange hats. Huh? Then you move and rearrange yourselves according to this group, and I want that it should still be, every group should have 1 color. You understand? The numbers 1 to 6 were assigned completely randomly. Then letters A to F were assigned completely randomly. Is it possible always to find, assign hats to people so that everybody gets 1 hat, and each group has completely different colors here also and here also, okay? Now, is this a matching problem? So, sorry, what's your name? Say that again. Shakti. And what's your number here? Sorry, 4. And what's your letter here? You didn't get a letter? Letter. Okay, so what's your name? RIA. Okay, what's your number? 4 and E. Yeah, so, no, just one of them. My idea is this. So, all right. What will we do? For every person, yeah, if the person belongs to this group here and that group here, so these you think of as your vertices, okay? There are now, look at everybody here and find out where they are in this table, okay? And yeah. Now, if there are two people here who are also in the same group here, yeah, there are two people who happen to receive the number 6, but they both happen to be in C. Then you add 2 parallel edges. Yeah. So this becomes a bipartite graph. Is that right? What is the total number of edges in this bipartite graph? If there are 36 students. 36 edges. Some of them may be multi-edges, but 36 edges. Each vertex has what degree? 6. Yeah. So each vertex has degree 6. What is the size of the minimum vertex cover? In this graph, if you want to cover all 36 edges, and in any one vertex, if it can cover only 6 vertices, and you have to cover how many edges in all? 36. How many? 6. So the vertex cover must have size at least 6. Do you also see a vertex cover of size 6? Are there 6 vertices which cover everything? Are there? Yeah, just take these 6. So the minimum vertex cover in this graph must have size at least is exactly 6. Now, our theorem says that the minimum vertex cover size is equal to the maximum matching size because of this theorem, with this algorithm, okay? It was an inequality, but I said that it's actually an equality because of this. That means this graph has a matching. So let me continue, you ask me again. So you draw this graph, no matter how randomly you assign, this graph will always have a matching. Why? Because the minimum vertex cover size cannot be less than 6. And since maximum matching size is always equal to the minimum vertex cover size, this graph has a matching of size 6. So what do? You find those 6 edges. They must be touching different things. Now each of those edges was placed because of some student. Okay, so you found 6 edges. Okay, all those 6 students, you take them away, give them red hats. Yeah, give them red hats. So there is one red hat, each of them, and since it was a matching, there is one red hat in each of them. Now, we still have 5 more hats, 5 more colors. But now this graph, what is the property? There are how many edges left in this graph? Sorry? 30. There are 30 edges left. And what is the degree of each vertex now? Because one person has left, it's 5. What is the minimum vertex cover? 6 again. 30 edges have to be covered with 5 each. So you will need 6. Minimum vertex cover is still 6. That means the graph has a matching of size 6. Find the matching. How do you find the matching? Using this algorithm. Find the matching. You found those edges. Identify the names of the students for those edges and give them yellow hats. They leave the game. Every vertex now has degree 4. The number of edges in the graph is 24. The same argument tells you that another matching and another matching and another matching, you would have found 6 matchings, one after the other. Okay? And each matching you will give hats of one color. Okay? Now, I don't think we have the time, but we have the hats. Okay? So, if you want, I mean, I don't know, the organizers can decide if you can, over homework, over dinner, show them the matching, then they will give you the hats. And you can take the hats home. The organizers are willing to sign it for you. Yeah? All right. So, just to let you know, the colors available are these. Yeah? I hope you find them attractive and you can take them home. Okay?
Come up and take your hats, but we require a witness, okay? We require you to come up with...
Yeah, so you can take it tomorrow, okay? So you should all, first of all, write down today in a sheet of paper this and, or actually in this break, is there a break now? No. Deepak is starting now. Okay, so please give them, write down this, yeah, put your names in on the 2 sides, okay? And somebody takes a picture, okay? And you people work together and show him 6 matchings. And if you show him 6 matchings, he gives you each a hat, okay? If you don't like the color, you can of course exchange amongst ourselves. No one gets the hat. Okay, so this theorem, sorry, I've told you 2 theorems. So in this theorem, it's called the Koenig-Eggerwari theorem. Koenig-Eggerwari theorem. It says in every bipartite graph, maximum matching, the size of the maximum matching, the best matching is equal to the size of the minimum vertex cover. And 1/2 of this equality, yeah, one inequality was obvious. We proved it in the morning. Which one? Which one is obviously smaller than the other? Maximum matching is always less than or equal to minimum vertex cover. That is always true. But the magic of this algorithm is that it is, the opposite is also true. That is, when this algorithm stops, it finds both a maximum matching and also a minimum vertex cover of the same size. And that's why they must be equal. Okay? Now, I said bipartite graph. What about non-bipartite graph? If the graph is not bipartite, what is the size of the maximum matching in this graph? What is the maximum number of edges that you can pick without conflict? Sorry? Can you pick 2 edges in this graph without conflict? 1. Yeah, so the maximum matching is 1. What is the minimum vertex cover in this graph? 2. So general graphs, this graph is not bipartite. This equality does not hold. For bipartite graphs, it's a miracle. Yeah, it always holds. Yeah, and if you, what I said was not very clear, but if you think about this algorithm and what happens when it stops, yeah, and like stare at it for 5 minutes, 10 minutes, 15 minutes, you will see that this algorithm actually proves this theorem. Okay, I'll stop now. Thank you very much. I thank the organizers for inviting me, and I thank you.
Thank you, Professor Jaikumar, for your amazing speech on the different matching algorithms, from the greedy algorithm to the Hungarian algorithm. I'm sure we all enjoyed it, and we'll definitely finish the matching and earn our hats rightfully.